Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at irrational numbers in geometry and measurement because they come up all the time. So we know pi is irrational, so let's look at using pi in measurement. So calculate the percentage error when finding the area of a circle with radius 8 centimeters if the rational approximation of 33 over 106 is used for pi. See, that's what happens when you're using irrational numbers in geometry and measurement. You often need to use rational approximations. In fact, your calculator does that. It will round pi to about 10 decimal places and then it stops. Well, a number with 10 decimal places and then it stops is actually rational. We can't get our calculator to store pi exactly because there are infinitely many digits after the decimal place. So we need to use rational approximations. So 333 over 106 is a rational approximation. It's the kind of number that might have been used a long time ago before calculators, but now calculators can get it right to about 10 decimal places. So 333 over 106 though, it actually equals 3.141509 and so on. Pi is 3.14159. So this one's kind of close. It has the first four digits right. So it's a rational approximation to pi. 333 over 106, a fraction with integer numerator and integer denominator is always rational. This is rational, this is not. We're using this rational number to approximate this. So if I was finding the area of a circle with radius 8, the exact answer, what it should be, is just going to be pi times 8 squared, so 64 pi. But if I use my rational approximation, instead of using pi, I'm going to use this. This is going to be 333 over 106. That's in place of pi times radius squared. So if I use this approximation, I would get an answer 201.0566 centimeters squared, but the exact answer should be 64 times pi, which is about 201.0619 centimeters squared. So you can see here that these two are very close. What would be the percentage error? Well, the absolute error is this minus this. So absolute error, we go this minus this, then we divide by the exact amount. So the exact amount, what the answer should be, is 64 pi, and then we times by 100 and stick a percent sign on the end. So putting all this in our calculation, we get about 0.003%. So 333 over 106 was quite a good rational approximation for pi. When calculating the area in this question, we got very close. All right, let's now look at using irrational numbers in Pythagoras' theorem. So remember, Pythagoras' theorem helps us find unknown lengths in right-angled triangles. So here we have C, the hypotenuse. If you're finding the hypotenuse, it's just the square root of shorter side squared plus longer side squared. Now, 2 squared, 4 plus 5 squared is 29. So the exact length for C is root 29. This is an irrational number. So if you're asked for exact form, just leave it as root 29 because this is exact. If we were to write it to any number of decimal places, it'd be inexact. All right, let's look at this question here. So this is 6 root 2, an irrational length. 6, let's find A. So we're going to use Pythagoras. When you're finding a shorter side, you minus. So it's going to be the square root of longer side squared minus the other shorter side squared. What is 6 root 2 squared? Well, 6 times 6 is 36. Root 2 squared is 2. 36 times 2 is 72. It's the square root of 72 minus 36, which is 6. Square root of 36 is 6. Turns out A is 6 also. And it turns out when you have a right-angled isosceles triangle, so two sides are the same, that the longer side, the hypotenuse, is always the square root of 2 times the shorter sides. All right, let's now look at using Pythagoras' theorem to construct line segments of irrational length. See, we can use Pythagoras' theorem to help us do just that. Let's say I wanted to construct a line segment whose length was exactly root 10. See, this would be pretty difficult because root 10 is about 3.1622. To draw a line segment exactly that length seems very difficult, but we can use Pythagoras' theorem. See, if we draw a triangle like this, with this side 1 and this side 3, this side will be the square root of 3 squared plus 1 squared, which is the square root of 10. So, because 10 is the sum of two squares, 3 squared plus 1 squared, we can construct side length root 10. That means we can find root 10 on the number line here. We can just rotate this triangle so root 10 lies on this line here. And so root 10 would lie about here. It's about 3.1622 and so on. So it turns out root 10 is what we call a constructible number. So constructible numbers are numbers that can be the side length of a line segment that can be created with just a straight edge, a ruler, and a compass. So all rational numbers can be constructed in that way. You can use a straight edge, a ruler, to construct line segments of 1 centimeter, 2 centimeters, 3 centimeters. Because you can divide line segments into parts, you can create line segments whose length is 3/5 or whatever. So all rationals are constructible. For any rational number, you can construct a line segment with that length using only a straight edge and compass. But what we've just seen from this example here with root 10 is that if k is constructible, so too is the square root of k. So the square root of any integer is a constructible number. So for example, square root of 3 is irrational, but it is constructible. Square root of 5 is constructible. Because the square root of 5 is constructible, then the square root of the square root of 5 is also constructible. But numbers like pi, cube roots like cubed root of 2, they are not constructible. So that's because when we're using Pythagoras to construct line segments, it involves square roots. It doesn't involve cube roots. It doesn't involve pi. So constructible numbers includes just all rationals and the square root of any other constructible number for our purposes. All right, let's now look at one final example. So we're going to calculate the area of this triangle in exact form. So once again, we're going to use Pythagoras. So I'm going to let this be h. Now, for any equilateral or isosceles triangle, you can divide it into two congruent right-angled triangles like this. And that, of course, means that this side here will be half of 16, will be 8. So h will be the square root of 16 squared minus 8 squared, which is actually the square root of 192. So the area is just going to be base times perpendicular height divided by 2. 16 divided 2 is obviously just 8. So the area here in exact form is 8 times root 92. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.